As we start to look at how Hadoop actually works, it's really important to understand why it works that way. A good explanation of that can be found in Eric Brewer's CAP theorem. This is a theorem of distributed processing that was introduced around year 2000. The CAP theorem looks at the core requirements of a distributed processing system, and it suggests that of these three core requirements, only two of them can be optimized at once, while the third has to be relaxed or abandoned. The three requirements are consistency, availability, and partition tolerance. And let's talk about what those terms really mean. If a system is consistent, it means it operates fully or not at all. And a good example of this that we're probably all familiar with is transaction commit rollback. So as we are going to update a system and we update three different tables, if we can't update all of the tables, then all the changes come back. So if we're trying to update an order detail table and an order header that has a total, if we can't update the details, then we can't update the header either. That would be a consistent system. Availability is what it says it is. The system is always available. So in a SQL system that's SMP, we might have a cluster so that if a node goes down, the other cluster node immediately takes over and answers requests. The third is partition tolerance. And by partition, we really mean that if we are in that MPP model, and in the previous lesson we said maybe a different server handles every month of the year, partition tolerance means that the system can still continue to run even if one of those partitions is down. A system that was highly partition tolerant would say that it's okay if the system still runs, we can still basically get the right answers even if a partition is down. So if we apply the CAP theorem to looking at the differences between SQL Server, say, and Hadoop, we get this kind of a view that in SQL Server, consistency is absolutely important. We have to have consistency, we have commit rollback, we have distributed transactions and so on. We have to get that. And we need availability, obviously. SQL isn't particularly tolerant about partitions being down. If we were to distribute our months over 12 different servers and one of the servers was down, we would, in a relational SQL Server environment, we would consider the database to be offline because it's not all there. Hadoop, as well as most other big data technologies, emphasize partition tolerance and availability and relax global consistency. So they're fundamentally different. And that means that in most big data systems, that traditional commit rollback really isn't a part of the system. So you might have eventual consistency, but you don't have to have consistency immediately and all the time. So in the SQL Server model, we're used to the ACID concept where we can rely on the consistency of data, we can rely on the integrity of transactions, and so on. We have to adjust our mindset a little bit with Hadoop, knowing that what it's trying to do is have thousands of partitions, and if it wasn't tolerant of one of those partitions being offline, then the whole system wouldn't work. It would become increasingly slow, difficult to manage, and so on. But what this leads to is that Hadoop and most big data technologies don't follow the same ACID concepts that most relational databases follow. Instead, they follow something that's kind of known as base. It's basically available, meaning not every partition is always going to be there, but eventually there will be consistency. And it's probably a review for you, but in the ACID idea, we can have distributed databases across a lot of nodes, but they have to be consistent before subsequent queries can be released to query them. And then we'll very often have two-phase commit for this. So we will get immediate consistency, but we also have some latency involved with that. We have to wait for distributed nodes to commit their data before the entire transaction can be committed and so on. So there's a little bit of a give on scalability there. Hadoop follows the base concept where it's willing to forego two-phase commit. It's willing to have a little bit less consistency across nodes. In exchange for that, it gets even more availability, gets even more scalability. And all this is well and good and it's fine, but we do have to kind of keep in mind that the nature of the data needs to be able to tolerate some of this imprecision in order to get that scalability. So if we do have something like, say, bank account balances being updated, base isn't a really good model for that. We really need ACID for that. So as we go through the technology and look at it, this is always good to keep in mind that these two technologies were designed with fundamentally different business requirements, and at some level we can't really mix those requirements together. So we can use Hadoop, but we need to use it where it really works well and where it applies, and not use it where we need some of the ACID kind of requirements around transaction control.